I think I'm audible now. Can you please tell me whether I'm audible or not? Okay, thank you. So let's proceed. Okay, so this is the data from the question, and Q is what we have to determine. So this R overall is equal to R1 plus R2 plus R3. R1 is for dirt layer and R2 is for R2 is for wall and R3 is for insulator. Okay, as this is a rectangular slab, we have given that it is an industrial slab, right? So I am considering that it is a rectangular slab. Okay, now for rectangular slab, what is resistance? X by Ka, right? This is thermal conductivity and this is area, and this X is thickness of the insulator. Okay, so for the dirt layer, we have from the question we have data, right? So yeah, from the question we are having it is 20 centimeters, and thermal conductivity is 1, and area is also they have given that we have to assume area as 1, right? So we are having area for this. So from the given question you will be substituting all the data in the given formula, and then you will be getting the overall resistance as 1.292 degrees centigrade per watts. Okay, so now we required overall heat transfer rate, right? So overall heat transfer rate is nothing but temperature difference by overall resistance, and this overall resistance we have calculated here. So this temperature difference is, as we are considering the overall rate of heat transfer, so the temperature difference is T1 minus T2, which is nothing but inner surface, like the temperature of the inner surface of dirt. Okay, after that outer surface of the insulator. So it is 900 minus 50 by 1.292, and after calculation you will be getting 657.9 watts. So this is the rate of heat transfer. So this is what he has asked in. Okay, I think you have no doubts. So let's proceed to another question. Okay, now this question is again from conduction, and here we are having a composite wall is made of two substances. So first of all, let us draw a composite wall which is of two substances. Okay, and one is 10 centimeters thickness and another one is 20 centimeters thickness with thermal conductivities of 0.05 and 0.1 watts per meter degree centigrade. Okay, and we are having data about ambient air also. Okay, so let us suppose that air is here and the temperature is 30 degrees centigrade. Okay, and the film heat transfer coefficient between the outer surface of the wall and the air. So as discussed yesterday also we have come across such type of problems, right? So from there we can say that in the solid, as the molecules are not moving, the heat transfer through this process will be conduction. Here also from this wall to this substance, it will be through conduction, and again from here to air. So here we will be observing movement of molecules, right? So whenever there is a movement of molecules and heat transfer is going on, so you can say that conduction process is observed. Okay, so so we are taking the heat transfer coefficient of of air is 20 watts per meter square degree centigrade. Okay, so the heat loss from outer surface is 165.4, means we have data about Q, right? And this is heat flux. You can say that it is heat flux because heat transferred per unit area, right? So here he is asking about calculate the inner wall temperatures and outer wall temperatures. Okay, so inner wall temperature means this one and outer wall temperature is this. So let us proceed. So this is the data from the question. Okay, right. From this problem, what you can see here through first wall and again through second wall and again fill. So these are series of connections, right? So here nothing but if we are calculating the overall heat transfer, then what you will take delta T by R overall, right? And this resistance, overall resistance will be R1 plus R2 plus R3. This R1 is from conduction between the first slab. Again R2 is for second one, and from R2 to R3 it will be this will be convection. Okay, so this is resistance for conduction of first one, resistance due to conduction, and this is R3 is resistance due to convection. Okay, so here again for convection it will be 1 by HA, and for conduction it will be X by KA, right? So as let us assume that area is 1 meter square, and heat transfer coefficient is given as 20. So each wall layer thickness, this is the thickness of the each wall, and this is the thermal conductivity of the respective slabs. So based on this, after calculating overall resistance will be 4.05. Okay, so this Q is equal to delta T by R overall, as discussed in the before problem. Okay, so Q is 165.4, and this delta T is for outer surface. Here we have taken this way, means see if we are considering this slab, this is T1, and for this air the temperature is 30 degrees centigrade, right? So as we are considering the overall heat transfer resistance, delta T will be T minus 30 by overall resistance is 4.05, and this is equal to 165.4 watts per meter square. As we are considering for as we are calculating the heat transfer rate for 1 meter square area of 1 meter square, we can take units as heat is equal to heat of rate transfer is equal to 165.4. Okay, so from this after calculating we are getting a temperature as 700 degrees centigrade. Okay, so the outside temperature of the flux of the wall will be 700 degrees centigrade. You can convert it into Kelvin. Whatever dimensions he have asked about, you have to select that option. Okay, so the next one will be what is the another one, inner wall temperature and outer wall temperature, right? So here we have calculated, already we have calculated outer wall temperature, and what okay, what is that we need, inner wall temperature, right? So let us consider that this film. Okay, so it will be again the rate of heat transfer in particular processes will be the same, means Q will be same in each process, like the rate of heat transfer in film, Q film is equal to Q1 is equal to Q2, right? So from this you can equate 165.4, so that is equal to T3 minus 30 by, and here as the process is convection, we can take resistance as 1 by HA, but here area is 1 meter square. So if you take area as 1 meter square, then you can take 1 by h, which is equal to 1 by 20, right? So that implies T is equal, after calculating again, rearranging this equation, you will be getting T3 as 38 degrees centigrade. Okay, so we have calculated inner wall temperature and outer wall temperature. So based upon here, we have nothing mentioned about dimensions of the temperature, but from the given units, see here also we are having watts per meter degree centigrade, and here also watts per meter square, here watt per meter square degree centigrade. So like we can guess that the temperature here you should select an option which is in degree centigrade. Okay, And while we were calculating these temperatures, if here he have asked about calculate inner wall temperature and outer wall temperature. So in an order, first of all you have to keep Ti and To. So if there are options like Ti is equal to like if you're having options as T naught comma Ti and none of these, so you have to select this option Ti and T naught, but not outer temperature and inside temperature. Okay, so this is the temperatures. Okay, so next problem. Now here we are having a composite wall of steel, mica and brick of thickness. So here we are having three slabs of different materials and different thickness. So thickness is also different for both of for all of the three. Okay, and so temperature at the surface of the steel. So let us consider this is steel and this is mica and this is brick, and the temperature at the surface of the steel is 200 degrees centigrade. Okay, so this is 200 degrees centigrade and the other end is 30 degrees centigrade. So let us suppose that we are having at the outer temperature, means the outside surface of the brick wall. Okay, so let us consider this temperature is 30 degrees centigrade and the total heat transfer rate is 100 watts per meter square. Means Q by A is equal to 100, right? 100 watts per meter square. And he is asking about calculate the effective thermal conductivity. Okay, effective thermal conductivity of the wall, right? So if we are about to calculate overall heat transfer, then what we will write, delta T overall by resistance overall, means overall resistance for this three materials. Okay, for the wall which is consisting of three materials, right? This delta T means 200 minus 30 and R overall, which is nothing but, as this is a rectangular slab, R overall means x by K, Ka, right? But here we are having data about Q by A. So let us remove this here. So let Q by A is equal to 200 minus 30 by R overall, which implies x overall by K effective, right? So what is x overall? What do you mean by x overall? X overall means the overall thickness of the wall, right? So this will be thickness of the wall, like thickness of the steel wall, which is 0.01, and again thickness of mica, which is 0.1, and thickness of the brick, which is 0.1, right? So from this calculation you will be getting thickness as 0.21 meters, right? By, sorry, this is x overall, right? And this is K effective. This is what he is asking, right? Calculate the effective thermal conductivity of the wall. So for calculating this, we should get what is R overall, right? So and this equation and this value we will be getting from this equation. See, from this equation we already have the data about Q by A and we already know about delta T, right? So which means 100 is equal to 200 minus 30, which is 170. As this is a temperature difference, we no need of converting this degree centigrade into Kelvin. Okay, so you can continue like this and by R overall. Okay, which is nothing but R is equal to 170 by 100, right? So overall resistance is 1.7. Okay, so what will be the units of overall resistance? We can calculate the units of overall resistance from this formula. See, this is watts, right? Watts is equal to, or you can take Q by A, watts per meter square. So Q by A we can take only when we are having an equal area for both of the, for all the slabs. If the area of the steel wall is same with the area of mica one and area of brick, then only we can take area outside of the overall resistance, right? Or else we can't take. So let's remove this here. Watts per, and here delta T, right? What are the units of delta T? Let us suppose it can be Kelvin or degree centigrade. And resistance overall. This is the, so R overall is equal to Kelvin per watts. So these are the units of overall resistance. Okay, so R is equal to Kelvin per watt. Okay, so we have data about resistance. So from this, what you will get? R is equal to 0.21 by K effective, right? Which is equal to 1.7. So K effective will be 0.21 by 1.7, right? So, and the units will be, let us check whether they are equating the units with like whether they are equating units or not. So this is for, this have meters, right? And the units of R is Kelvin per watt, right? So what will be this? Watt, sorry, watt meter per Kelvin for 1 meter square, for an area of 1 meter square, right? So what will be that? Watt meter per Kelvin meter square, which is nothing but watt per meter Kelvin, right? So these are the units of thermal conductivity. So after all, so K effective will be 0.21 by 1.7 watts per meter Kelvin. Okay. So next one. So till now, whatever we problems we have covered are from conduction part only, and each part is different. See, from the first question we are calculating overall resistance, and from that we are calculating overall heat transfer, right? And from the second question, here with the help of the overall resistance, we are calculating inner wall temperature and outer wall temperature. So this is second type of model, okay? And the third model is, again this aim, we are having composite wall slabs, and for this we will be calculating the overall resistance, and from that we are calculating effective thermal conductivity, right? So these are different types of models in conduction in slabs part. Okay, so these are only few models, and in this we will be asking about spheres also. They may include spheres. So till now we have discussed about only rectangular slabs, right? So there is a chance of asking about spheres also, and again we are having another model for conduction, from conduction. So wall of a house which is 10 meters wide and 15 meters high. So this is 10 meters wide and 15 meters high, is made from 0.5 thickness. Okay. So this is 0.5 meters thick brick wall, and the thermal conductivity is 0.02 watts per meter Kelvin, and the surface temperature on the inside of the wall is 20 degrees centigrade, and that on the outside of the wall is 5 degrees centigrade. Calculate the heat flux through the wall and heat loss to the wall. So this is very simple. See, let us consider that heat is transferring from this side, means, so this is the thickness of the brick, 0.5 meters, and this is the width of the brick, and this is the height. As the heat is transferring in this direction, so this will be the area which is to be calculated. So what is, this is a very simple question. What is heat flux means? So heat is nothing but minus Ka into temperature difference between the two wall of the slab by thickness of the slab or the path along which the heat is transferring, right? So we can calculate this, right? So K, which is 0.02 into area of the slab into temperature difference, which is where is the temperature difference? Yeah, this is 20 minus 5 by thickness of the slab is 0.5. Okay, so we are having this Q. Q by A is nothing but heat flux, right? So which is 15 by 0.5. So this is the heat flux means, and the units will be watts per meter square. And rate of heat transfer is nothing but heat flux into area, right? So what will be the area? It is the 0.02 into 15 by 0.5 into 10 into 0.5. This is the area because this is the projectional area, right? So which is thickness, and this is 10. Okay, so this area will be covered. Okay, so whatever the calculations, after calculations I think you will be getting 3 3 watts. Okay, so 3 watts is the rate of heat transfer, and the flux will be 6. I think it will be 6. Yeah, 0.6 watts per meter square. So this will be 0.6 watts per meter square, and this is the solving solution part. So next we are jumping. So till now we have covered different types of models from conduction, and now we will be introducing into some new concept, which is lumped heat capacity. And we will be discussing, this is a very interesting topic and very easy topic. So from this we can guess at least at least one question definitely we will be getting. Either that will be a theory part or that will be a solution part. Okay. So here we are having a ball of 50 diameter, which is cooled by exposing it to air stream at 320 Kelvin. And under these conditions, the conductive heat transfer coefficient is 100 watts per meter square Kelvin, and estimate the time needed to cool steel ball from 1120 Kelvin to 720 Kelvin. So due to the high thermal conductivity of the steel, there are no temperature gradients within the ball. Means as the conductivity of the steel is very high, wherever you observe the temperature, it is the same. Means there is a uniform distribution along the ball, inside the ball, right? So this is the main condition for lumped heat capacity condition. Okay, means here there will be no resistance from conduction part. There will be only resistance because of convection. Okay, so from this we are having, we'll discuss how this formula is derived. Okay, so this is the formula for lumped heat capacity. I will discuss only about the terms. So this is the temperature at a particular time, and this is the ambient air temperature, and this is the initial temperature of the ball, and this is the ambient air temperature. So here H is heat transfer coefficient, and T is the time at which like we want whenever we are considering this type of cases, sometimes we need to find time at which the temperature is 30 degrees centigrade, or find the time at which the temperature is 20 degrees centigrade. So we'll be having different terms and different temperatures where we can stop the process, right? So to find this time, we will be having this minus ht, and m is mass, so cp is heat capacity. Okay, so from this, here he have given about air stream temperature, right? So we are having already data about T infinity. So T infinity is 320 Kelvin, and H is also given. H is 100 watts per meter square Kelvin, and estimate the time needed to cool steel ball from Initial temp means initial temperature is 1120 Kelvin, which is nothing but T naught to T at particular time. T is equal to temperature at particular time T is equal to 720 Kelvin. So here I have given all the three temperatures, and heat transfer coefficient and ambient like density is also given. So density is 8000 and heat capacity is 450 joules per kg Kelvin, right? So already we are having the data about these things. So from the formula, what we need about mass. So mass is nothing but density is equal to mass by volume, right? So mass is nothing but density into volume of the sphere. As the volume of the sphere means 4 by 3 pi r cube, right? And I think we are having data about the diameter of the sphere. So R will be 25, right? So from this, after we can substitute like T is equal to 720 minus 320 by 1120 minus 320 is equal to exponential of minus 300 into time by density into 4 by 3 pi r cube into 450. Sorry, I think I missed. Okay, so this is HAT by MCP. Okay, from this you will be calculating. After substituting all the data, you will be having the formula. We will be getting value for time, right? So T is equal to 207.94 seconds. So this is the time at which the temperature of the ball is 720 Kelvin. Okay. So next one, heat exchanges. So what is the given data? Water at the rate of 6800 kg per hour is to be heated from 311 Kelvin to 328 Kelvin in a double pipe heat exchanger by using another water stream in the annulus. So here we are having an annulus. Okay, so inside one liquid is going and out, and the outer annulus part, outside of this part, I mean between these two pipes, another liquid is going. Okay. So the hot water enters the annulus countercurrently at the rate of 3400 kg per hour and at 366 Kelvin. So he is asking about the overall heat transfer coefficient. Okay. So as it is a countercurrent one, let us draw the diagram. So first of all, whenever you are solving a question, you have to exhibit the data. So countercurrent direction. So TH will be, this is hot water, right? It is 366. So at the entrance 366 Kelvin, and again at TH naught it is not given about TH naught, but the data about cold temperature is there. So at the entrance it is 311 Kelvin and at the exit it is 328 Kelvin, right? So first of all, for calculating the overall heat transfer coefficient, we have the formula of Q is equal to UA delta T LMTD, right? So this delta T LMTD can be solved only if we are having all the temperatures, and first of all we have to check whether uh, TH naught, like whether there is delta T2 or not. See, if delta T1 is equal to delta T2, then delta T LMTD will be average of these two temperatures, means delta T1 plus delta T2 by 2. Okay, so this will be the logarithmic mean temperature difference. If we are having a difference between delta T1 and delta T2, then only we can take like if we are having difference between approaches temperature of approaches, then only we can take a logarithmic mean temperature difference, right? So for that we have to equate the heat rate of heat transfers for hot fluid and rate of heat transfer of cold fluid. So at steady state, what happens? What of the heat that this hot fluid is losing will be gained by the cold fluid, right? It means nothing but the rate of heat transfer is the same. So QH is equal to MCP, delta T of hot fluid is equal to MCP delta T of cold fluid, right? So this delta T is nothing but So we are having data about mass of the cold fluid and mass of the hot fluid also, and Cp will be the same because the Cp depends upon the material, right? So here the two types of materials are the same, which is water, and you will be getting 3400 kg into 366 366 minus T, which is equal to 6800 kg per hour into, what is the temperature difference? 328 minus 311. Right? From this we'll be getting the temperature of hot fluid at the exit. So this will be 328 minus 311 by 3400 minus plus 366, right? So after calculating this, you will be getting, so from this calculations, you got this TH naught as 332 Kelvin, right? So from this, you will be you can calculate UA delta T LMTD, right? So Q is equal to UA delta T LMTD, and you can calculate delta T LMTD, which is nothing but difference of approaches divided by ln of delta T1 by delta T2. Okay, so this delta T1 is nothing but difference of this hot fluid, entrance of the hot fluid and exit of the cold fluid. Okay, so here delta T2 is exit of the hot fluid and entrance of the cold fluid. So this is delta T2 and this is delta T1. So you have to calculate this and equate it with MCP delta T. So what is the question? Overall heat transfer coefficient. So this is nothing but this heat is nothing but MCP delta T, right? So this delta, and this can be for hot, either can be for hot fluid or cold fluid. As it is at steady state, we can take any of them, right? So based upon upon substituting all these values, you will be getting the overall heat transfer coefficient as 1296.3 watts per meter square Kelvin. Okay. So again, another one. So here we are having hot oil at 200 degrees centigrade is used to preheat a cold fluid at 45 degrees centigrade in 1:1 shell and tube heat exchanger. So we are having a 1:1 shell and tube heat exchanger. Okay. And this exit temperature of the hot oil is 110 degrees centigrade. Heat capacity and flow rate of fluid and oil is same, and heat duty is 2 kilowatts. So here we are asked to calculate overall heat transfer resistance if it is a counter current flow, right? So first of all, we are having data about it is data that it is a counter current flow. So and the temperatures are 200 degrees centigrade and to preheat a cold fluid at 45 degrees centigrade. So we have no and the exit temperature of hot oil is 110 degrees centigrade, right? So the temperature of the hot oil we have and temperature of cold fluid. So let us consider that here we are having 45 degrees centigrade. So we have no data about exit temperature of cold fluid, right? So this is for hot fluid, THI and TH naught, and this is TCI. So we have no data about TC naught. So before problem also we are having the same, like we have to calculate the overall heat transfer resistance, right? And here we are already having heat duty. So from this Q is equal to MCP delta T. Let us consider that this is for cold fluid. So what you will get, 2 kilowatts means it should be 2000, right? 2000 is equal to Cp of fluid and okay, or you can we are having no data about mass, right? So let us consider that we heat capacity and flow rate of fluid and oil. Here we have given that heat capacity and means MCP of fluid and is same with the MCP of water, right? So while equating QH is equal to QC, you will be getting T1 THI minus TH naught of hot fluid is equal to TC naught minus TCI of cold fluid, which is nothing but, what is THI? 200 minus 100 is equal to TC naught. We don't know about this TC naught, and it is 45. So from this you will be getting 100 plus 45, which is nothing but 145 degrees centigrade, right? So this will be 145 degrees centigrade. If it is a counter-current flow, this is the temperature profile. But here we are asked about calculate the overall heat transfer resistance if it is a co-current flow, right? So if it is a co-current flow, what happens? See, this is for 200 degrees centigrade and this is 110 degrees centigrade. So this is entrance of the hot fluid, right? And here this is the entrance for cold fluid, means TCI, which is nothing but 45, right? This is low, 45 degrees centigrade, and the exit temperature of the cold fluid is at 145 degrees centigrade. Means it is exceeding the, it is, so by this process he meant to say that the cold temperature, the cold temperature fluid is exceeding the outer temperature of the hot fluid, and it is gaining a temperature of 145 degrees centigrade, which is not at all possible, right? So this process is not at all possible, as at steady state what happens, the amount of heat transfer should be the same for both the cases, right? So if you consider this condition, we are having a temperature of 145 degrees centigrade, which is greater than TC naught, which is greater than TH naught, which is not at all a feasible condition, right? So for this question, actually this is an options question, like we had options of 1, 2 and infinite, and D is impossible. So we have to select an option which is giving like it is impossible. For this process is impossible. Okay. So next problem. This is also the same, right? Here he is asking about what is the area needed for a counterflow heat exchanger, and by what percentage the area would be increased if it is a parallel flow. So this is a solution that you guys should solve. So this will be a work for you that I am giving. So this is a countercurrent flow and this is a parallel flow, which is nothing but co-current flow. Okay. So first of all, you have to calculate the same temperatures. If we are not having data about the all the temperatures, first of all, you have to equate the rate of heat transfers for hot fluid and cold fluid, and then from that you have to get the data about the required temperatures. So from that you will be getting again Q is equal to UA delta T LMTD, which is equal to MCP delta T. So this MCP delta T you can consider for either hot fluid or for cold fluid. Okay. So based on this, you will be getting overall heat transfer resistance, or I think here we are already having this heat transfer resistance. Yeah, we are having this HI on the water side, including the cooling factor, is 11,000 watts per meter square degree centigrade. So here we have to calculate overall heat transfer resistance, which is nothing but 1 by H plus 1 by HF. Means here as he have given already, as he has given about falling factors also, you have to include resistance that is happening because of this falling factor, right? So you have to include this also, and you should calculate U from this. After that, you will be getting U overall resistance, and you have to substitute in the above formula like this one. So from this you will be getting the area. Okay, and by what percentage the area would be? Second question will be the area would be increased if it is a parallel flow. Means again you have to do the same process for co-current flow and find the area, and percentage increase is nothing but 1 minus A of co-current by 1 A of countercurrent. into 100. So this will be the answer. Okay. So 12.68% is the increase in the heat transfer. Okay. So let's just proceed another question. Convection plus radiation. See, here we are having a horizontal steam pipe of 20 meters long and 60 external diameter, and losses are 135 kilowatts at to the surroundings at 310 Kelvin. So heat is 135 kilowatts and ambient air temperature is 310 Kelvin, and pipe is of length 20 meters long and diameter is 60 which is nothing but 60 into 10 power minus 3 meters. Okay, and then we are having heat transfer coefficient as a function of temperature, right? And the Stephen Boltzmann constant is also there. Now we have to find the emissivity of the bare surface of the pipe, right? So here we are having steam is flowing in this pipe, and it is in contact with ambient air temperature also. So this is 300 Kelvin and the pipe carries steam at 500 Kelvin, right? So as the steam is at 500 Kelvin, you can say that the process is convection process and radiation also, because here we are having a huge temperature difference, like the steam is carrying that we are carrying is at a very high temperature, right? So at very high temperatures, the heat transfer process can be called as radiation. Okay, so for convection it will be formula is HA into delta T, which is nothing but T minus T infinity, and for convection and for radiation it will be A sigma emissivity into T1 power 4 minus T infinity power 4. See, here we are having not only the temperature difference, we are having the powers, fourth power of temperature, right? Means here you have to mention the temperature in Kelvin only. If you consider only temperature in degrees centigrade, then it will be wrong. So T1 power 4 means here we are having temperature as in Kelvin only. If we are having 500 degrees centigrade, then what you should take? 500 plus 273 power 4. This is what you should take. But as here we are already having this temperatures in Kelvin scale, there is no need of taking in converting into Kelvin scale. Okay. So from this formula and this, what is the heat losses? We already have the data about heat losses, right? So the equation will be 135 into 10 cube, which is equal to, what is the transfer coefficient? 1.65 into delta T power 0.5 into delta T, right? Means we can say that delta T power 1.25 plus area. Okay, so we can take out area. We can take out area from the whole formula, and sigma is 5.87 into 10 power minus 8 into sigma, and T1 power 4 means 500 Kelvin, 500 power 4 minus 310 power 4, right? So after and this area will be, so what will be the area of the steam pipe, right? What is the area of the steam pipe we can get? There it is. Wait. 2 pi r, right? This is the area of the steam pipe. So after substituting all these values, you will be getting the emissivity of the base surface as 0.8. Okay, so this is how we will be solving the process. So here we have to consider convection process and radiation process, and from that you will be calculating emissivity. So here another question is about radiation. So here we are having three infinite parallel plates. So let us consider that this is plate 1 and this is plate 2 and this is plate 3, and plate 1 is maintained at 1227 degrees centigrade, and plate 3 is maintained at minus 175 degrees centigrade, and there is no data about the temperature of plate 2. Okay, so let us consider that the temperature of the plate 2 as T2. Okay, and the emissivity of both the bodies is equal to that of a black body, right? So emissivity of 1 is equal to emissivity of 2 is equal to emissivity of B, and plate 2 is placed between plate 1 and plate 3. So here what is the temperature of plate 2? So as he has given, there are three infinite parallel plates, and they are of the emissivities of both the bodies is equal, right? It means which is nothing but the heat that is getting transferred between plate 1 and plate 2 is equal to the heat that is getting transferred between plate 2 and plate 3. So here we have to use Stephen Boltzmann's law, which is sigma A emissivity into T1 power 4 minus T2 power 4, right? So the sigma value is same for both the cases, and emissivity is same for both the cases, and the area is also the same for both the cases, which means let us consider that Q12 is equal to Q23, means T1 power 4 minus T2 power 4, which is equal to T2 power 4 minus T3 power 4, right? So you will be getting T1 power 4 plus T3 power 4 by 2 whole to the power of 1 by 4, which is equal to T2, right? So this is the plate of the this is the temperature of the second plate, right? So this T1 temperature, see here we are having T1 temperature 1227 degrees centigrade, right? So we have to convert this into Kelvin, means 1227 plus 273, which is nothing but 1500 Kelvin, and it is 175 Kelvin, means 273 minus 175, which is 98 Kelvin, right? So it will be 1500 power 4 plus 98 power 4 by 2 whole power 1 by 4. So after this is the temperature of the second plate, and after calculating you will be getting temperature of the second plate as 1261.5 Kelvin. Okay, so this is the answer. Okay, Rambilas Kumar, you are 12th standard, and I think you will also be having a few topics about heat transfer, but about the slabs, I don't guess you will be having these topics. Okay, so let's skip to another question. So in this question, you will be having about the evaporators. So in detail, we'll be discussing about the evaporators in the course structure. Okay, so here it is desired to concentrate a 30% salt solution. So initially the concentration of the, sorry, okay, uh, for this session you can, from this session you can get data about heat transfer, loss of heat transfer, like what is conduction, what is convection, and what is radiation. So I don't think that this session will help you a lot, but you can get some idea about what kind of processes that will be happening in heat transfer. Rambilas Kumar, I don't think this session will be much useful for you for your JEE session. Okay, so now let us get into this question. We are having the initial concentration of the solution is 0.3 and final concentration of the solution is 0.4, right? So considering a feed of 300 kg per minute at 30 degrees centigrade. So feed temperature, like feed flow rate, is 300 kg per minute, and the temperature of the feed is 30 degrees centigrade, right? So the boiling point of the solution is 110 degrees centigrade, and the latent heat of vaporization, so we are having data about lambda 2100 kilojoules per kg, and specific heat of solution is 4 kilojoule per kg Kelvin, right? So what he is asking about the rate at which heat has to be supplied in kilojoules per minutes to the evaporator. Okay, so first of all, if you are considering an evaporator, so you will be providing feed over here, feed initial section, and feed will be collected over here. Let's just consider that it is of F naught. Okay, and here you will be giving the steam, right? So this is the process. So if you consider a component balance, then what you'll get, mass of the feed into percentage of the amount which is there, like percentage of salt in the solution at the entrance is equal to the mass of the feed at the outlet and percentage of the solution at the outlet, salt solution, right? So see, from this data we are having mf, we already have mf, mass of the inlet flow rate, as 300 kg per minute, and mass of the product is what we need, and this is the percentage of solution, means 40% solution, right? So this is the mass of the product, 225 kg per minute, and this 225 kg per minute, you should mention the dimensions also, because we are taking mass flow rate of feed as kg per minute, right? So obviously you have to mention product also in kg per minutes. And heat, so in this heat what happened is, here we have to, the rate at which heat is to be supplied to the evaporator is, means here we are asking about steam, right? No, we are asking about Q, which means heat to increase the temperature, increase the temperature of the feed, so that its solution will be changing from 30% to, concentration of the solution will be changing from 30% to 40%, right? So which is nothing but mass flow rate of the feed, mcp delta T plus steam. This is the energy of the steam, right? So energy of the steam is m lambda. This is mcp delta T, right? So m is mass of the feed, which is 300 into 4 into temperature difference is, yeah, 110 minus 30, which is nothing but 80 degrees centigrade, right? So after substituting this, you will be getting the heat rate of heat transfer as 2.535 into 10 power 5 kilojoules per minute. Okay, so this is the amount of heat that we require for the process. Okay, so these are the different types of questions that we will be getting in heat transfer, and we can now from tomorrow the course of heat transfer part 1 is going to start. So if you will be able to access those courses only if you take plus subscription. So use my code padma10 and you will be getting 10% discount off, and you'll be having mega quizzes and weekly quizzes and doubt clearing sessions also. So please stay tuned.